Yep. 15, 1, 5. Okay. Were you able to successfully calculate the magnitude of the electric field from that 4 nanocoulomb charge? What'd you get? Sorry? 1.44? 144? Newtons per coulomb. Direction, it's positive, so it would be up. Yes? Right? Because the location is right here. Would not a positive be repelled? Much like I am when Shashan shows up late? Repelled. Did you get the electric field for the negative 2 nanocoulomb charge? 72, I think. Direction, a positive right here would get pulled that way. So that way. Right? My actual directions are up and that way. So it's going to look like this. 144 plus 72. The resultant, here's your electric field. Okay. Now, quick refresher. Do you remember last day, will I give you 2 charges and say find the electric field between them on the written section of your test? Yes. Will I give you 2 charges at angles like this on the written section of your test? No. This would be perfectly fine as a nasty multiple choice. And in fact, because it's a nice right angle, I would also have no problem saying don't just find the magnitude, find the direction as well, because I think it's tangent. It's not sine law or cosine law or anything crazy like that. Is that okay? So you got the Pythagoras, okay?
Yeah.
Opposite adjacent, yes? It's going to be inverse tan of opposite over adjacent. Yeah, that's okay. By the way, it's really the inverse tan of 1/2 because 72 over 144 is a half. 26.5, what of what? (26.5 degrees, what of what? East of north, which is the same as 63.5 degrees north of east. They found that angle, which is also fine. They drew their triangle with the 72 first and then the 144 next. I didn't. Right? Same angle. Is that okay? Any others? Okay. So, key idea here today. For the vectors, we have to figure out the direction either ahead of time or afterwards. For forces, we use like charges repel, unlike charges attract. For electric fields, we use which way would a positive want to move that could. We add them vectorially. Today, we're looking at scalars. We're going to look at potential energy. And if I've done my job right, Akemi, it's going to seem very familiar. Hopefully you're going to say, this looks like an awful lot like gravity, if I've done my job right. Except, it's going to break down. Stuff can fall up. Sorry. But for scalars, since there's no direction, we are going to put negatives and positives in. Say what? I'll show you what I mean.
What?
Touche. What happens in lesson 3? I actually combined lesson 1, 2, and 3 into lessons 1 and 2. Shorten things a little bit. Had to pick up some slack somewhere. So what we're going to look at today is electric potential energy. And just like last unit, remember when we went cosmic with gravitational force, we said, sorry, MGH is not going to work. We're going to need some kind of cosmic electric potential energy equation. So we define electric potential energy in a manner similar to gravitational potential energy. We say that electric potential energy reflects the work that must be done to move a charge, little q, from a point near the charge. Can you cross this out and make this a big Q? Out to infinity. You see, there's several possibilities. It's possible, Graydon, that this charge is positive, This charge is negative. Which way does this charge want to fall? Towards the negative. So I would have to do work if I wanted to move it up to infinity. I would have to push and push and push and push and push. But the further away I got, the easier it would be, yes? And eventually out at infinity, where there's zero potential energy, then I could let it go and we'd be okay. That's if the charges are opposites. Or, if the charges were opposites, I could start out here, give it a little tap, drop it, and it would start to fall. And as it fell, the potential energy would become kinetic, 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 kinetic. In fact, that's really the equivalent of this, dropping a tennis ball. If they're unlike charges. Or they could be like charges. Now, if they were like charges, if these were both negatives, let's say, which way does this guy want to move? Wants to fall up. So here's where the analogy breaks down. It would want to fall up. In fact, it must have some potential energy right now, and as it falls away, it's going to speed up, speed up, speed up. The potential energy is going to turn into what kind of energy? Speeding up, speeding up. What kind of energy? Right. Kinetic. This is a job for conservation of energy. I'm trying to give you some of the questions we can handle. Or, if they're both negative, I could start out here at the edge of the universe, and I could start to push and push and push. It doesn't want to go this way. I have to do work. I could say, how much work, how much energy does it take to get it to go closer and closer and closer and closer and closer and closer, and when do I got to stop? Or, instead of starting out here at rest, I could throw it so that it has some kinetic energy, but as it gets closer and closer and closer, what's going to happen to its speed if it's being repelled? I could ask you, when does it come to a stop? How far away? When does all of the kinetic for a split second become potential? All sorts of variations on a theme that we can do. Let's look at a few.
Does electric current work the same in space?
Does electric current work the same in space? Yep. Yeah, I think the temperature plays issues because colder wires are less resistive than hotter wires, and I know that if you're on the sun side, I suspect they have to really insulate them. But in terms of what I think with the way you're asking, in 0G, I think is what you're really asking when you mean by outer space. Yeah, that doesn't affect current at all. Temperature does, though. Recall, just like with gravity, the force between two charges is also not constant. It varies with distance. What we really need is the area underneath the force versus distance graph, and to find it, we really need calculus. I'm going to give it to you. K, big Q, little q over R. That's potential energy, electric. Hey, what's that look an awful lot alike? The gravitational potential one, except there's no negative here. The reason there's no negative here is, unlike gravity, stuff can fall up too. So trying to always define it in a certain way doesn't work. But everything else, I think you know. K, SAMP, 9 times 10 to the 9th. Big Q, the planet. Little q, whatever you're moving around. R, how far away you are from them. Okay. By this relationship I wrote down here, the energy is 0 at infinite distance. Those of you that are in calculus, if you take the limit as r approaches infinity, this will work out to 0. So out at infinity, no energy. By this relationship now, energy is a scalar. For scalars, we're going to put in the positive and negative signs. Remember, for forces and fields, I actually told you that sometimes they write the equations with absolute value signs around them to let you know, don't put negatives and positives in. We decide the directions. Gianluca, for scalars, we have to put the signs in. And here's a dumb way to remember it. Are you ready? Listen close. We're going to write this down later. Forces and fields, forget the signs. Scalars, put the signs in. You have to keep that straight. Otherwise, you'll get the wrong answers. But I'll show you another way to keep it straight as well. Don't write that down just yet. What that means is, if you put, unlike charges, negative and a positive, right now that means this guy has negative potential energy, which actually works okay, because if I want to move this guy out to 0, he must start out at negative, because I would have to add energy. I would have to do work. He wants to fall left if that's negative and that's positive. I would have to add work, do work, add work, do work, add work, do work, add work, do work, add work, do work to get out to 0. So it works, no pun intended. Turn the page. Next page over. Read along with me. It says this: find the potential energy of a negative 75 microcoulomb charge that is 3 centimeters away from a positive 120 microcoulomb charge. B, write a work energy equation if we move it out to infinity, assuming they begin and end at rest. And then C, find the work done by the applied force. You might recall I mentioned to you that my friend who typed this up typed it in Word 95 for Mac. This unit is where some of the graphics start to glitch. That is supposed to be microcoulombs and microcoulombs and microcoulombs and micro. When you see that smear, assume it's microcoulombs, unless I say different. Courtney, I need to retype every single diagram. I've put it off for 3 summers because it's going to be about 200 or 300 hours of work, and I just, I'm not looking forward to it.
Do a couple diagrams a day.
In 60 days, there's probably about 4,000 diagrams. I'll let you do the math as to how many I would need to do per day.
No, it's a work in progress.
Uh-huh. Through all these? Well, you think about it, how many lessons I do, about 80 lessons. How many diagrams are there in each lesson? About 15 or 20? 80 times 20 is 3,200. Oh, no, I didn't include the ones that are actually in the homework, did I? Ooh. So, it's on my list of things to get to. I just don't like you guys good enough to have done it this year.
You didn't know it yet.
Ready? What does part A want me to find? Potential energy is K, big Q, little q over R. By the way, if you don't have your formula sheet out, you should. Can you all get your formula sheet out for a second, please? See, here is part of the problem with this unit. What letter on your formula sheet do they use for electric field? E. What letter do they use for potential energy? Okay. This is why I don't use E for energy, because I knew already at the beginning of last year in Physics 11, I'm going to come to electrostatics and electric field, and they're going to get them mixed up. I wish they would use PE. Now, I know why they don't, because that's technically 2 letters, and why would you use 2 letters? That should suggest 2 separate variables. So I'm technically doing it wrong, and I'll accept that, but I think it's clearer. For what it's worth, listen closely. First row, forces, fields, forget the signs. Second and third row, scalars, put the signs in. That's another way you can remember as well. You can't write this on your yellow's formula sheet because you're not allowed to write anything on your yellow formula sheet. Erase that. Eventually, I'll look for it. Okay? So, it wants us to find the potential energy. K, 9 times 10 to the 9th. Big Q, that's the bigger charge, and we're going to assume when they talk about a fixed charge that some invisible angels are holding it in place, or maybe it's thumbtacked to the paper or something silly like that. So the charge that ain't moving is the 120 micro times 10 to the negative 6 Coulomb charge. We put the negative in for the scalar quantities in this unit. We put the signs in. Divided by 0.03. How much potential energy does that negative 75 microcoulomb charge have at that location right now? I can get something in the thousands, I think. Or I could be wrong. First of all, it has to be negative because I see positive times negative times positive. Negative 2,700 joules. Yeah, I ignored you. Sort of like our offense. Why negative? Because where is 0? Infinity. So if I have to add energy to get to 0, I better be starting out with a negative number. And it doesn't want to go to infinity. It wants to fall towards the positive. Okay, so that works. Cole, can you read B to me, kiddo?
Write a work energy equation.
Write a work energy equation. You know what? Work is the change in potential plus the change in kinetic. We can't use force times distance. Why not? Because the force is changing every split second, every split meter that you travel. It's not the area underneath the graph because there ain't no graph. So it's our third definition of work, which has now become actually our go-to definition last unit and this unit when you're dealing with changing forces. Hey, are any of these zero? Why can I do this? It says in brackets, assume we start and end at rest. Don't have to. I could certainly easily include that. C wants us to actually find the work done. Okay. Change in potential. What's change in anything? What is the final potential energy? Where are we ending up? Out of infinity. What's my final potential energy? 0. Minus. What's my initial potential energy? And you'll notice I do get a minus in terms of the amount of work that I have to do. I have to add energy to this system. Otherwise, it's not going anywhere. I get a minus. I do get a positive answer, which makes sense in terms of the physics. It's saying, hey, you want to get it out to infinity? Not enough energy to do that right now. Somebody better add some energy to this system in order to accomplish that. Is that okay? Next page. So by this relationship, like charges, if they're both negative or if they're both positive, like charges have positive potential energy. This makes sense because you have to do work to get them to overcome the electrical repulsion and push the charges together. It makes sense because what's my energy out at infinity? If I'm falling, I must be losing energy. To get to 0, I better start with a positive amount so that when I fall, I end up with 0. Or, if I want to start at 0, I have to push it in close. I have to add work to get it to go there. So example 2 says, find the work required for an external agent. By the way, when they say external agent, my physics prof used to always just say, just pretend it's little invisible angels or something is moving it. Pretend it's your hand if you really want to do that. But some outside external agent is adding energy to this system. In this system, energy is not being conserved because there's an outside source. To place a positive 2.5, ooh, careful, not micro, milli, which is 10 to the negative 3, Coulomb charge, 5 meters away from a positive 1.75 milli-Coulomb charge. Assume the 2.5 milli-Coulomb charge is initially an infinite distance away. Brett, what's this question asking me to find? How about find the word find and then read me 2 words after that?
I'm looking right now. I'm having a hard time here.
Yeah, find the word find.
Yep, looking. Find the word.
So what's it asking me to find?
Work.
Thank you. Really?
Yeah.
Took you that one?
Yeah, well,
I don't know.
we'll probably do it.
Totally care. Work is the change in potential plus the change in kinetic, yes? And let's assume we start and end at rest. I forgot to type that in that question, but I think that's fair game. Alejandro, what's change in anything? Change in anything? Help them out, folks. What's change in anything? Huh? Yes. Can't forget that. Not allowed. Sab, smack him one. Oh. Are any of those 0? Why? Okay. You won't always be. I could certainly give you a question where you start somewhere. It'd just mean more typing on my calculator, right? Yeah, and we've defined infinity to be 0. I could start 10 meters away, in which case you would have some initial energy. That's fine. But now this is going to be K, big Q, little q, all over. And I guess it's going to be R final, because that's what's changing. Question, Graydon? Question?
No.
No. Are you sure? You're doing okay? Speaking of K, what's K? 9 times 10 to the 9th. Big Q is the fixed charge, 1.75, not micro, milli, 10 to the negative 3. Little q is the moving charge, 2.5 times 10 to the negative 3. All over. Final distance, final radius is 5. How much work does it take? You get 7875? That's to 4 sig figs. So 7,880 to 3 sig figs. Units. Direction. Someone challenge me. Come on. Direction. Someone challenge me. Why is there no direction? Energy, scalar. Okay, don't fall for that. No direction. So, here is the key concept you need to take out of this besides just the number crunching. Zach, for energy, a scalar, we will include the plus or minus of the charge in the actual equation now. Unlike forces and fields, the first row, forget the signs, absolute values. For scalar quantities, we include the signs. See, unfortunately, it's going to get a bit more confusing because next lesson, we're going to look at voltage. Unfortunately, they don't call it voltage. Voltage is a modern term. The term for voltage is potential. Not potential energy, potential. So on your test, I will be asking you to find the potential. And a bunch of kids, Courtney, are going to read potential energy, and they're going to be crunching this, and I got to give them a 0 because that's just like if I said find the acceleration and you gave me the length. Nice that you did it, but that's not what I asked for. Nope, I will sometimes, but not always. And that's because that's what they did on the provincial, and I haven't really changed my test since there is no provincial yet because I don't like you guys that much. Also on my list of things to get to is retype all my exams and things. Now, we've looked at, Austin, how much work if you have some kind of external force moving things around. What if there is no external force? Then energy will be conserved. Or, here's, I think, my trigger phrase that I gave you guys, Vlad. I said, are they asking for how much work? And you would have said no. I would have said, is there a change in height? Is there a change in speed? Then this is a job for conservation of energy. There's a reason why I brought that phrase out last unit. Because that's also going to occur in this unit. As an example, example 3. An electron is originally 2.5 times 10 to the negative 11th meters from a proton, and at rest, you know what? I think that's probably important. It is released and moves directly towards the proton. Find its speed when it's 1 times 10 to the negative 11 meters from the proton. Does that make sense? Right now, which way does this electron want to move? Direction. To the left? Okay, towards the proton. By the way, what direction is the electric field right there? To the right. The electron wants to move to, there's another way you can figure out the direction of electric field. Which way does the electron want to move? The other way is which way a positive would want to move. Okay? Find its speed. So here's what I would say, Rob. Is this question asking me to find the work? Say no. You know how I know? Can you see the word work anywhere in the question? So, ready? Scene 1, act 1, take 2. left-hand action. Rob, is this question asking me to find the work? No. What's it asking me to find? Is there a change in height? Yes. Is there a change in speed? This is a job for? Okay, there's our trigger. By the way, I said height. Hopefully you were clever enough to say I'm flipping it on its side, but we're still going to pretend that it's falling down or falling up because I think we think better that way when it comes to gravity. Is that okay? So, oh, so are any of these 0? Potential energy, don't be using MGH. We're not talking gravity here. We're talking what's making it fall? Electric potential energy. It's going to be kinetic energy. Hey, that hasn't changed since physics 11. What's kinetic energy always? Half mv, and I'll call it final squared since it's kinetic energy final, plus k big Q, little q, all over our final. Rob, what did you say we're trying to find? The nerd within me would like to algebraically try and get the V by itself, but it's going to be ugly. So instead, I'm not going to do it all at once. I'm going to move the final potential energy by subtracting it over to this side. I'm going to rewrite this equation as follows. Initial minus final equals a half mv squared. And now, I'm going to start plugging in numbers. I'm going to get an answer on the left-hand side. Then, Seb, I'll divide by m times by 2 square root. But to try and do this all at once is going to be yucky. Trust me. So, k. 9 times 10 to the 9th. Charge 1. It's a proton. Please don't disappoint me. Please don't disappoint me. What, Brett? Negative 19. Charge 2. It's an electron. What? Ah, thanks for remembering to put the sign in. Yeah, negative 1.6 times 10 to the negative 19. All over our initial. It's in the actual word problem. What's my initial radius? 2.5 times 10 to the negative 11. And that's going to be minus. Same thing, same thing, same thing, all over our final. What's our final? Also in the word problem somewhere. That equals a half mv final squared. Let's evaluate the whole left-hand side. And I'm going to use the same trick as we did for gravity, Nathaniel. I'm going to type this in, get an answer, and then just backspace. And I think all I need to change is that bottom number, and it'll be way less typing, get an answer. And I'll carry everything to as many sig figs as I can for a while here. So typing in the first one, I'm going to get 9 times 10 to the 9th times, 9 times 10 to the 9th times 1.6 times 10 to the negative 19 times negative 1.6 times 10 to the negative 19 divided by 2.5 times 10 to the negative 11. So my initial potential energy, I get negative 9.216 times 10 to the negative 18. Minus the final amount of potential energy I have. I just got to change that to a 1.0, right? I think, yeah? Negative 2.304 times 10 to the negative 17. That equals a half mv final squared. I'm running out of room. If you guys have more room, keep going down. I'm going to go to the next page. Do you guys, is it the next page on the same page for you guys still? Okay, so I can do that one. If kids print it, they won't freak out. I'm going to type in the left side. So I'm going to go negative 9.216 times 10 to the negative 18 minus my answer from that's still stored. I do notice I get a minus minus in the middle there, which is a, I think it's going to work out positive. I hope so, because I kind of want a positive spin here, right? Hey, it did. I get 1.3824 times 10 to the negative 17. 1.3824 times 10 to the negative 17. That equals a half mv final squared. Kemi, how would I get the v by itself, kiddo? Times by 2? Which mass? It's an electron! Please don't let me down. Please don't let me down. You mean that's on there somewhere? It's on there! No, folks, one of my huge peeves, this is how I find out kids haven't done the homework. On the test, I'll be doing, by the way, what we're really doing here is particle collisions and particle physics. I will be giving you protons and electrons in questions on the test. And one of the things that will drive me crazy, I'll see a kid write a question mark for the mass of a proton or an electron or its charge. It's on your sheet. That's how I know they didn't do any of the homework and never clued in. But let's just not do that. It's all on your data sheet, yes? So it's going to be, this is a particle collider, what we're doing here. We're colliding a proton and electron, basically, right? Two times 1.382 times 10 to the negative 17 divided by the mass of an electron. What is it? I know it's 911. It's 9.11, but I can never remember the exponent. Negative 31? Thank you. So 2 times this divided by 9.11 times 10 to the negative 31. What the? That's faster than light. Oh, square root. Whew. The speed of light's 3 times 10 to the 8th, and I was getting 3 times 10 to the 13th. Say what? Square root. Still pretty fast, but that's okay. I've never seen electrons travel. You can't follow them with the naked eye. They travel fast. 5.5 times 10 to the 1, 2, 3, 4, 5, 6. Units, it's a speed, meters per second. In fact, in particle collisions, Rob, energy is conserved. What they're doing at the Large Hadron Collider is they're smashing particles into each other at extraordinarily high velocities. They know how much energy there was before the collision. They add up how much energy there was after the collision. And if it doesn't add up, a new particle must have been created. That's how they found the Higgs. Except they're doing it, Chase, with incredible, incredible, incredible accuracy. Kemi, can you wait for 30 more seconds just so I can give you the homework? Okay. I'll come back to example 4 in a second, but first of all, if you got folks want to, you can circle the homework. This is the homework that I assigned my block A. 1, 2, 3, 5, 6C, and 8. I'll say that again when I circle it on yours. 1, 2, 3, 5, 6C, and 8. Now you can go, Kemi. The rest of you, take a look at this last one here, example 4. I'm not going to give you one this ugly, but I'm just going to talk you through it. First thing example 4 says is, find the potential energy of this system. Okay, I would find the energy between these two, include the signs, but it's a scalar. I would find the energy between those two, include the signs, but it's a scalar. I would need to find this distance, which I could with Pythagoras. Then I could find the energy between those three, include the signs, but it's a scalar. Add them up. Too much work. No pun intended. But I'm not going to give you something like that. That's overkill. B says, find the force on this top charge. I have no problem asking you to find the force on one charge from two others, but this is yucky. It's not going to be a right angle, because if you find the force here, it's being repelled up. Add that tip to tail too. If you find the force here, it's being yanked down at an angle. Rob, you got a triangle up, down. It's going to be sine law or cosine law, because there is no right angle. I'm not going to give you one that ugly. That's overkill. But as a scholarship question in the old physics days, this would have been great, because I haven't done anything new yet so far. It's just been yuckier math, right? What does C want me to find? The electric field right there. Okay, I would find the electric field magnitude and direction from this guy, and it would be to the right. I would find the electric field magnitude and direction from this guy, and it would be down. I would add those two together, tip to tail, get an answer. Then I would find the electric field magnitude and direction from this guy, which would be up diagonally. I would add that to my previous answer, tip to tail. It'd be lots of trig. Could I do it? Sure. That's overkill. So, in theory, Rob, no problem. In fact, in theory, give me 6 or 7 charges. I can do it. The energy is the nicest one because it's a scalar. You don't have to worry about the trig as long as you get the distance between them. Okay, you have to do a little bit of trig sometimes, Pythagoras, to get the distance between the two diagonal charges, but I could deal with that. Not going to give you one that yucky. So in your homework, number 1, totally fine. Mr. Dewick, you said you weren't going to give us one this yucky. Hey, energy is a scalar. You have both the distances. There, you don't have to do any trig. Find the first, find the second, add them up. Include the signs. Number 2, find the work. 3 is good. Find the speed. I think change in speed, change in height. This is a job for conservation of energy. Oh, Vlad, please notice milli. Just pointing that out. Uh-huh. Pardon me?
Like, will there just be like on the test? Will it change?
Will what change?
Like the milli and the nano. And
I would have, I don't think I'll give you nano. It'll almost all be micro, but sometimes just to get nice numbers, I might do a milli because I'm a nerd and actually like answers that are legitimate. Number 5, find the work. Number 6, the reason I skipped A and B want you to find the initial force and the final force. You know what? C says find the work, and you can't use force because the force is changing, so just use change in potential plus change in kinetic, but I think that kinetic is 0, so change in potential. And then number 8, find the net electric force, find the net electric field, and those are all microcoulombs, even though the diagram looks kind of wonky. That's a good review of the last 2 lessons. Okay. I didn't assign those, but you could practice those if you wanted to.